Recently, thermodynamics has become the center of much attention between quantum gravity and quantum mechanics and gravity. And in particular, certain principles, like the holographic principle, upper bounds for entropy have been introduced because the entropy of a black hole is supposedly 10 to the 20 times that of the thermal radiation of the sun. All these things, though, have no foundation thermodynamically. So I want to show that you cannot put on bounds to entropy. Entropy increases, and there is no limit that can be applied to it. We start with a combination of the first and second law, commonly known as the Gibbs equation. E is the internal energy, T is temperature, S is entropy, P pressure, and V volume. Okay? It's a combination of the first and second laws. What I want to do now is to convert that into a differential equation and solve it along certain characteristics, paths, which are known as adiabats. So, I want to change the dependency now to T and V. So, I take the derivative with respect to V. Okay. Then I introduce Maxwell's relation. Okay? And then an equation of state. An equation of state known as the Brunei's equation of state, which is PV is equal to S E. This can be derived from the Virgo theorem, and it says that S in the ultra-relativistic state is equal to 1/3. In the non-relativistic limit, it's equal to 2/3. Okay? So I can insert this into here, and when I do, I come up with the equation for the internal energy. Okay? Many years ago, Lagrange devised a method for solving this equation along certain characteristics. And these characteristics are given by the total derivative the first relation I get is T V to the S is a constant from here, and the second relation P V to the S is equal to a constant. Two particular solutions to the equations. And along these paths, system is adiabatic. How do we see this? Well, first we can write the general solution as E is equal to V minus S times phi V S. Where phi is an arbitrary function. If phi is equal to 1, we have what we call a system which shows repulsive character. Okay? An example is a Fermi gas at low temperatures, which is repulsive even equal to 0. If phi is equal to 1 and S is equal to 1/3, I come out here, but phi is equal to the power 4 minus 1/3, T to the 4th, V to the 4/3, which is equal to T to the 4th, V, which is Stefan's law of black radiation. So this goes the whole gamut of solutions to the energy equation. Now, I can rewrite this equation in terms of the entropy. ds is equal to 1 over T dV plus P over T dV. And I can show, or better writing it, plus P dV. I multiply here by V to the S. V to the S, T, a constant, is adiabatic condition. Temperature falls as the volume increases. And from this, I can write here V to the S, V to the S, VE. P, remember, is plus SE times V to the S minus 1 in dV. And this is a total derivative. Yes, what we obtained here. So the entropy can be written as an arbitrary function of T, V to the S. Anywhere the entropy is constant, V T to the S to any power is constant. Okay? So for adiabatic change, we have S constant, and these are constant. Now, the entropy is a function only of the internal state of the system. It's not a function of the transitory motion of the system or rotation. Why? Because if I can move the system faster, and the entropy would increase or decrease, I would have a preferential state where I can visualize the motion as in terms of the entropy. And that cannot be done. For a black hole, they write the first law of thermodynamics, St ds is equal to dE minus omega j minus v dq, where j is the angular momentum, omega the angular velocity, charge, and electrostatic potential. This is impossible. The entropy is not a function of angular momentum. For the same reason, it can only give information about the internal state of the system. It cannot say, I cannot increase entropy by increasing the angular momentum as a whole of the disk. So this is completely incorrect. Okay? In 1948, a relatively unknown paper was published and then almost completely ignored, in which there appears a dichotomy in that equation, in which as the temperature goes to 0, okay, certain behavior can become apparent. One is repulsive behavior between the particles, in which E is equal to a constant times E to the minus S, which is none other than this adiabatic law here. Okay? And dE, dV is less than 0. Okay? This is one type of behavior, 0. Another type of behavior is that the system will condense, in which case P is equal to a constant T to the 1 plus 1 over S. Okay? And in this case, dE, dV is positive. Only two types of behavior possible. And as a corollary to this theorem, I can show that that equation, fundamental equation, splits into two equations. One characterizing the mechanical system, and another characterizing the thermal system. So these two become distinct. Here I have no knowledge of entropy nor temperature. Here the system becomes independent of the volume, and that means condensation means I have a phase equilibrium. Okay? So, I can define the entropy density is equal to E plus P minus mu n divided by T, a Euler relation. N is the particle density, mu the chemical potential, if we want to introduce one. And I take the total derivative of both sides, and I get ds is equal to E plus P is the entropy density. So I would have 1 over T, the H, the N, if I divide through by N on both sides of the equation, plus H over N, D, 1 over T, minus mu, D, 1 over T, minus 1 over T, D, mu. Plus I can add on and subtract a term, 1 over T dP n plus minus 1 over n T dP. I've added 0 to them. And I can combine the equations, terms, into two equations. One is 1 over T d H n minus 1 over n dP, okay, plus 1 over n H minus n d 1 over T plus 1 over T dP minus n over T mu. Okay? And I claim that this is the mechanical part. T is factored out. This is the thermal part, where the number of density is factored out. And just to show you that the first equation is a mechanical equation for a perfect fluid, you can consider the Einstein equation, one of the Einstein equations, in which he introduces the conservation of energy. dE in dt, this is the evolution in time, is equal to minus 3e plus p dr t dt divided by r. R is an expansion factor. The volume goes as r cubed. Okay? It's a radius of the universe, whatever. So I can transpose 3 here. Three, 1/3 is just S that we had before, the Grunheisen factor, and this becomes dP in dt. Okay? This is just minus H. Okay? And now I can multiply this equation by r cubed, the volume. Okay? And from this, we can get d r cubed in dt plus p dr cubed in dt equals 0. Now, if we don't know what that equation is, we can compare it with that equation above. And if we do, we come out with T ds is equal to dE plus P dV. Divided through by dt doesn't change anything. This term is the same as that one. This term is the same as that. And therefore this is identically equal to 0. Why a perfect fluid should be used to model the universe is a good question. But his relation can never take into account the thermal radiation involved. This is the thermal part, and that is the mechanical part. This term here, S is 0, constant. This term is nothing other than the Clausius equation, which describes equilibrium. Putting mu equal to 0, I have h dt over t squared equals plus u over t. And this is the Clausius equation. dt over t is equal to h over t. The entropy density. And that imposes a thermal equilibrium. Okay? Now, we discussed the first and second law. Let's go to the third law. The third law says that the entropy goes to 0 when the temperature goes to 0. A necessary condition is that dE in dV at T constant is not equal to 0. If we take an ideal gas, E is equal to Ct, and this will not show any tendency to condense. It is beyond an ideal gas. So we need T goes to 0, Cv goes to 0, the heat capacity at constant volume, and the third law says that S will go to a constant, which is Nernst's form, or S will go to 0, which is Planck's form. Thermodynamically, we can only measure differences in entropy. Therefore, we can have no possibility of distinguishing Planck's or Nernst's law in this case. So, S is equal to minus the derivative of the Helmholtz free energy with respect to temperature, which is equal to dS in dV at T constant in dV plus a constant. Again, using Maxwell's relation, this is dP in dt, a V constant in dV plus C prime. Okay? So, in one case, this case, dP and dt is equal to 0. And in the other case, dP and dt is equal to 1 plus 1 over S C T to the 1 over S. And in both cases, this term goes to 0, and we are left with S being a constant. Again, Nernst, it's a constant different from 0. Planck, it's equal to 0. So it's just a matter of choice. Okay, this is the review of thermodynamics. that we need. Now, we want to go on and discuss entropy bounds for black holes, or a universal entropy bound. That is, can entropy be bounded? According to Clausius, there are two laws. The energy of the universe is constant, and the entropy tends to a maximum. A maximum with respect to what? With respect to any constraints imposed on the system. And in his popular lectures, he used to talk about the heat death. Heat death means that any time you have entropy, two systems of different temperature, put into thermal contact, entropy will flow, heat will flow from the hotter to the colder body. And we can see the universe being divided into many, many pieces of unequal bodies. And each time there's a flow of heat from hot to cold, there will be production of entropy. And this will increase without bound until the universe reaches a state where equal temperature, and it will no longer show any evolution to evolve. What state is that? Depends upon what universe we're talking about. But it has nothing to do with the bound. About 40 years ago, they came up with an expression for the entropy of a black hole being proportional to the area of the horizon. And that entropy was huge, 10 to the 20 times the thermal entropy of the sun. So it was believed that that would be the all-ending entropy of any system. So it seemed not too preposterous to think there is a common denominator between the two entropies of like origin, and how can we express one in terms of another? Entropy also has a meaning of information, or lack thereof. So in some sense, this type of entropy, which is geometrically an area of something, should be a container for information, bits of information. Okay? And that bit, so it was formulated into a holographic principle in which the description of a volume of space can be thought of as encoded onto a boundary of the region, preferably like light boundary, like a gravitational horizon. The entire universe can be seen as a two-dimensional structure of information painted on a cosmological horizon. Okay? And therefore, the maximum information that we can have about anything would be 1/4, why 1/4? The area of the horizon. So it was proposed that the entropy, the ratio of entropy to energy, was bounded by some radius divided by h bar c. K is called Boltzmann's constant, h Planck's constant, c velocity of light. Now, what can we think of a radius? It could be a thermal radius, thermal wavelength. And since we are in the ultra-relativistic area, because c appears, we can introduce the thermal wavelength in that region, which makes it equal to 1 over t. Okay? And we know that 1 over t is the s in the E. So this ratio should be bounded by ds in the E. Okay? If we look at black body radiation, for instance, we come out with S over E is equal to 4T. And if we make the temperature small enough, this can become as large as we like. So it was hypothesized that the temperature of black body radiation cannot become, temperature cannot become very small. is a limit. There is no limit. From Wien's law, we know that the maximum, where the curve of the spectral density peaks, this is a constant. And there is absolutely no condition on the temperature for the thermal spectrum of black body radiation. So what are we talking about there? Well, if this applies, then to normal systems are those in which S varies as e to the n, where n is less than 1. Degenerate systems. And in this case, the second derivative of the entropy is negative, meaning that it's maximum black body radiation. Black body radiation, n is equal to 3/4. Okay? But it's proposed that the entropy of a black hole would vary as e squared. Okay? In this case, we have an unstable situation. Heat capacity is negative. Heat capacity related to the second derivative of the entropy. And therefore, this universal bound should encompass this case and this case together. Okay? That this should hold for both cases. And this is clearly impossible. Why? Because this function is concave and this function is convex. And the defining property of entropy is that it is a concave function. S over E is a decreasing function. And this I will show you now. Concavity can be expressed if I have two systems, one of energy E1 and one of energy E2, okay? And I have a lambda, which is greater than 0, but less than or equal to 1, a parameter. Concavity says that S of lambda E1 plus 1 minus lambda of E2 must be always greater or equal to lambda S E1 plus 1 minus lambda S E2. Okay? And I can use the property now that as the temperature goes to 0, the heat capacity goes to 0, energy will tend to 0. And in this case, I can envision, in any general case, I can envision that if I plot S versus E, the ratio of S to E is a straight line going through the origin, and I can set either one of the two energies equal to 0. If I set E2 equals to 0, then I have S of lambda E1 greater than S of lambda E1. Okay? E1 now is everything, so I can just leave it without the index. And now, if I divide by lambda, it's a positive quantity, and divide through by the energy, this says that the entropy is a decreasing function because this gets smaller and smaller. Lambda is less than 1, so this. Okay? And in this case, we have that tangent anywhere along the curve is less than the ratio of S over E. So we have this inequality inverted. Okay? Normal entropy. Notice also that the derivative here is vertical. So ds in dE is equal to 1 over t, which is equal to infinity, meaning that as the energy goes to 0, the temperature goes to 0. Now let's look at the other case where that inequality could hold, as in the case of the black body, black hole entropy. We would have S E, this type of behavior, where at the origin ds in dE is equal to 0, meaning that T is equal to infinity. So as energy goes to 0, the temperature goes to infinity, and this violates the third law of thermodynamics. So such a behavior cannot occur. Even if such behavior could occur, this would no longer be a universal bound. Why? Because normal entropies don't obey it. So all this is based upon the concavity of the entropy. Okay? Now, finally, let's look at this holographic principle and see what it says. Well, before I do that, I want to show that there is a bound to the derivative of the entropy. And that is precisely the ratio of that. So I have ds in the E, the derivative, which is less than or equal to S E plus H minus S E divided by H. Finite difference of the two. And I can write E plus H is equal to lambda minus 1 E, which is greater than E. And if I introduce that into the above, I have ds into E, S lambda minus 1 E, minus S E, divided by lambda minus 1 minus 1 E. I can multiply through the bottom by lambda and the top by lambda, so that becomes 1 minus lambda, lambda, lambda. And we know from before that if I put here lambda minus 1 this way, that this is greater than that. So I can write this now as S of E, 1 minus lambda divided 1 minus lambda. That cancels with that. And we see that, in fact, the derivative of the entropy is bounded by the ratio of S over E, showing that this inequality has to be inverted. Now, so the idea that the amount of information that could be encapsulated in any region is not only finite, it is proportional to the area of the boundary of the region measured in Planck units, and the relationship that the number of bits of information the observer can gain cannot exceed 1/4 of the surface area has no meaning. First, entropy is not defined on a geometrical object like a disk. Entropy is defined, information entropy is defined on a probability space, a sample space with random experiments, measurable sets of events, and the probability of those events. Where is the geometry in all this? There isn't. A typical case is the Shannon entropy. You've all seen this. With the PI, it's a complete set of probabilities varying between 0 and 1. And this entropy has the property of being subadditive. That is, if I have two probabilities, I have log P1 minus P2 log P2 greater than P1 plus P2 and this is the property of subadditivity. Well, you could say, why don't we use this property to define entropy? But this property can be obtained precisely from the concavity condition. How do we do this? Well, we say that if we again put this E2 equal to 0, we have S E greater than lambda S of E. If we put the opposite, E1 equal to 0, we have S1 minus lambda E greater than 1 minus lambda S of E. And now I want to add the two of them. This becomes S of E1 plus S of E2 equals S of E1 plus E2. Concavity, same as that. So therefore, subadditivity, sorry, concavity is more general. So I can say also that concavity plus the third law implies subadditivity. And this is the defining property of entropy. It has nothing to do with a geometrical object. And what it says, in effect, that a chord connecting any 2 points of the entropy curve always lies below the curve. Okay? And there's no bound.